So you're thinking of taking up skiing, but of course you don't actually own skis. And skis are somewhat expensive. Besides buying skis, you can also rent skis. Renting is not that cheap either, but it is certainly cheaper than buying skis. So the question is, do you rent skis or do you buy skis? It's a tricky question. If you buy skis and end up using them to ski many more times, then you've justified your purchase. On the other hand, if you buy skis but don't actually ski that many more times afterwards, it'll end up being a waste of money. So the tricky part is making a choice now or on a daily basis without knowing how the entire future will play out. The right decision depends on some factors that we don't really know yet. Here's a different setup that may also happen to you. Maybe you just finished grad school, took a full-time job, and thinking about buying a car for the first time. Or you can just be lazy and use Uber or Lyft everywhere, and maybe get a bike for your daily commute and use a phone to order your groceries. Do you buy a car or just crowdsource everything on the fly? Here's a motivating problem that shows up in building computer systems. Hard drives, at least until recently, are big and bulky. There's some startup time to actually getting a hard drive going from rest because it has to spin up a disk. After using a hard drive once to fetch some data, should you keep the disk spinning hoping that another request comes in, or should you shut it down right away and try to conserve energy? Of course, the hard drive is just an example, and this question arises with many components in a computer. This type of setting may be even more relevant now as we move towards more heterogeneous systems, as well as greater emphasis on other concerns like power consumption. We'll stick to the buy or rent problem for skis to keep things concrete. Suppose it costs K dollars to buy a set of skis. For simplicity, we'll assume K is an integer. Let's say it costs $1 to rent skis for 1 day. Let L denote the total number of days you end up skiing. Now the tricky part is that we don't know the value of L ahead of time. Each day, we have to decide if we want to rent skis or finally buy them without knowing if it'll be the last day we ever end up skiing. If we knew the value of L, the number of days we'll ever end up skiing, then the problem will be much easier. If L is less than or equal to K, then we should rent every single day, as we won't end up skiing enough to justify the cost of buying them. If L is greater than or equal to K and we do end up skiing a lot, then we should buy right away on the first day. There's no sense in wasting any money on renting. The optimum value, in hindsight with full knowledge of L, is always the minimum of K and L. The problem is we don't actually know the value of L. The goal is to develop an online strategy where we make decisions 1 day at a time that is competitive with the optimum value in hindsight. I'll start with a warm-up question. Can you come up with a too competitive algorithm for this problem? I'll give you a hint that the algorithm is relatively simple. It's worth pausing and thinking about. I'll give 10 more seconds. So how to get a too competitive algorithm? On each of the first K-1 days, rent. If any of those happen to be the last day you ski, then you're optimal. If you find yourself skiing on the Kth day, then buy. Sure, now the solution in hindsight would have bought on the first day, but you're still within a factor of 2 of the optimum solution. As a thought experiment, suppose I added a little bit of flexibility to our purchasing options. Suppose you're allowed to buy one ski at a time for K over $2 each. And suppose you can also rent one ski at a time for half $1 a day. Now you still have to have a full set of 2 skis each day. But now you can pursue hybrid sort of strategies where maybe you buy one of the skis and you rent the other. So let's try to figure out what the optimum value would be in hindsight with these additional options. It's worth pausing to think about this for a moment. If L is less than or equal to K, then you should still rent a full set of skis every day. If L is greater than or equal to K, then you should still buy both of the skis on the very first day. It turns out that the added flexibility doesn't help, and the optimum value in hindsight is still the minimum of K and L. We now turn to online algorithms. Can we use the added flexibility of buying or renting one ski at a time to improve upon the 2 approximation ratio that we got previously? So here's one approach. On day 5K over 8, buy the first ski. And then on the Kth day, buy the second ski. So in between those 2 days, you're renting just one ski to complement the one ski you already bought. So when we try to figure out the competitive ratio, if the total number of days turns out to be 5K over 8, then we pay 5K over 8 from renting both skis for that many days, plus K over 2 for buying one of the skis on that day. That adds up to a total cost that's 9/5 times the optimal value. If L is equal to K, then we pay the cost of renting both skis for 5K over 8 days, plus the cost of renting just one ski for 3K over 8 days, plus the cost of a full set of skis, which all adds up to 29 over 16 times the optimum value in hindsight. The days in between, if you work it out, will actually have slightly better approximation ratio than either of these 2 dates. The point is that being able to rent or buy one ski at a time allowed us to get an even better competitive ratio. If you can buy half a set of skis at a time, then you can improve the approximation ratio to something better than 2. Similarly, if you can buy 1/4 of a set of skis at a time, then the competitive ratio would improve even more. If we take this thought experiment to the limit, then we might consider a model where you can buy any arbitrary fraction of skis and rent any arbitrary fraction of skis each day. We frame a continuous version of our problem as follows. Let x sub 1 denote the fraction of skis that we buy on the first day. Like maybe you buy 10% of the skis on day 1. Let x sub 2 denote the fractional amount of skis that you buy on day 2. Like maybe you buy another 5%. So on and so forth, we let x sub I denote the fractional amount of skis that we buy on day I. For each day I, we let y sub I denote the remaining fractional amount of skis that we rent. We can write our problem as a continuous optimization problem as an LP as follows. The total cost that we want to minimize is the cost of the keys times the fractional amounts we buy each day, x1 plus x2 up to xl, plus the cost of renting each day, y1 plus y2 up to yl. The basic requirement is that we have a full set of fractional skis each day. So for each I, we must have x1 plus x2 up through xi, which represents the total ownership at day I, plus y sub I to be greater than or equal to 1. First, let's try to figure out the optimum value of hindsight in this model where we're allowed to take fractional skis. It turns out that if L is less than or equal to K, then we should still rent each day, in the sense that we set all the x's to be 0 and all the y's to be 1. If L is greater than or equal to K, then we should still effectively buy in the first day by setting x sub 1 to be 1, the remaining x's to all be 0, and all the y's to be 0 as well. It turns out that the optimum value, even with the added flexibility of fractional skis, is still the same, the minimum of K or L. We now look for online algorithms. And in particular, we'll analyze algorithms as a particularly structured form. Each day I, we're going to set x sub I to be 1 over k times the sum of x's before day I, plus delta over k for some parameter delta to be determined. So for example, x sub 1 will be delta over k. We'll set each y sub I to be as small as possible, which is 1 minus the sum of x's through day I. An interesting property of this update rule is that the ownership of skis is exponentially increasing over time. If we take the update rule for x sub I and we add the sum of x sub 1 up to x sub I minus 1 to both sides, then we get that the sum x sub 1 plus x sub 2 up to x sub I, which represents the ownership at the end of day I, is equal to 1 plus 1 over k times the sum of x's from 1 to I minus 1. This represents the total ownership at the end of the previous day plus delta over k. As for the cost of this update rule, each day we pay k times x sub I plus y sub I, which when we substitute in, the k's cancel out, is equal to the sum of x1 through x sub I minus 1 plus delta plus 1 minus x sub 1 minus x sub 2 minus up to x sub I. We subtract out more x's on the right in red than we add in blue on the left, so this is all less than equal to 1 plus we know that the optimum solution pays 1 per day for the first k days. That means that for the first k days, we're 1 plus delta competitive with opt, and as long as we can ensure that we own the skis by the kth day, then we'll be 1 plus delta competitive overall. So now we want to choose delta to be as small as possible to ensure that we own a full set of skis by day k. That means we want the sum x sub 1 plus x sub 2 up to x sub k to be equal to 1. If we think about how this sum works, each day we add delta sub k, and we also multiply the pre-existing sum by 1 plus 1 over k. So each of those added delta sub k terms keeps growing exponentially by a factor 1 plus 1 over k each day. So the additive delta sub k from the last day, day k, doesn't get multiplied at all, but the delta sub k from day k minus 1 goes up by 1 plus 1 over k. The delta sub k from day k minus 2 goes up by 1 plus 1 over k squared. The delta over k term from day 1 ends up getting multiplied by 1 plus 1 over k to the k minus 1. So this is a geometric series, and overall we get delta times 1 plus 1 over k to the k minus 1 plus 1 over k. Rearranging and solving for delta, we get that delta is equal to 1 over 1 plus 1 over k to the k minus 1 plus 1 over k. This might look a little complicated, but when k gets sufficiently large, this converges to 1 over e minus 1. Overall, we get a competitive ratio of 1 plus delta, which converges to e over e minus 1 for large k. So we get this competitive ratio that converges to e over e minus 1, which is about 1.582. This is much better than the factor of 2 that we started with. This is promising. But the original real-life model doesn't actually allow for buying fractional skis. The remaining challenge is how to turn our fractional ski solution into discrete buy or rent decisions. We can get a fractional solution to the buy or rent problem with a much better competitive ratio of about 1.582. But at the end of the day, we don't want a fractional solution. We want a discrete solution of whether or not to buy or rent on each day. To facilitate this transition between continuous and discrete, we introduce randomization. The idea is to interpret each x sub I as a probability of buying the full set of skis on day I. Similarly, each y sub I will be interpreted as a probability of renting skis on day I. The way to do this is fairly simple. We first pick a value alpha between 0 and 1 uniformly at random. We also simulate the fractional algorithm from previous, And in particular, we generate these values x sub 1, x sub 2, x sub 3 of fractional skis we're supposed to buy on each day. Each day, if the sum of x's up to that day becomes greater than or equal to alpha, then we buy the skis. We can visualize this algorithm by imagining a partition of the unit interval by the x's. We pick alpha somewhere random in this interval, which falls in one of the x's. Here it fell into the slot for day 6, which means that for days 1 through 5, we rent, and on day 6, we buy. So let's analyze this algorithm. The probability of buying on day I is equal to the probability of alpha landing in between x1 plus x2 up to x sub I minus 1 and x1 plus x2 up to x sub I, which is equal to x sub I. So then, the expected cost from buying skis is equal to the sum over each day I, the probability of buying it on day I, times the price of skis k, which is equal to k times x sub 1 plus x sub 2 up to x sub L. Now, for renting, the probability of renting on a day I is equal to the probability that alpha is greater than the sum of x sub 1 plus x sub 2 up to x sub I, which is equal to 1 minus x sub 1 minus x sub 2 up to x sub I, which is exactly how we define y sub I. The expected cost of renting is equal to sum over all the days of the probability that we rent on that day, which is equal to the sum of y sub i's. Overall, our expected cost is equal to the expected cost of buying skis plus the expected cost of renting skis, which is equal to k times the sum of x's plus the sum of y's, which is exactly the cost of our fractional solution. This means that our randomized algorithm gets the same competitive ratio as the fractional solution, about e over e minus 1. So that's how we arrive to our final algorithm. We first solve a continuous version of the problem, where we get a better competitive ratio when we're allowed to buy fractional skis on each day. We then use randomization to convert this fractional solution into a discrete randomized buy or rent decision. At the end of the day, we get a competitive ratio of about e over e minus 1, which is much better than the factor 2 that we started with.